All right, good evening all. Good evening all. You're welcome to the tutorials with From Eternity the Schoolboy. Today, take a look at physics. Today we'll take a look at physics. As usual, we starting the physics, the WAEC physics syllabus from the beginning. So we'll start from the concept of matter. So the topic is what? Concept of matter. Concept of matter. Here you see almost or similar things with what we mentioned, what we discussed in chemistry. But it's not exactly from the same perspective. The physics will not go so deep as what we met in chemistry, but you hear some things we discussed in chemistry. So, without wasting time, we go into, of course, what is matter. We know what is matter, right? We know what is matter, right? Yes, matter is anything that has what? Mass and occupies what? Space. Matter is anything that has mass and occupies what? Space. Okay, so matter is anything that has mass and does what? Occupies space. Now let us now look at the structure of matter. Structure of matter. From research, a lot of research works have proven that matter is particulate in nature. What it means that matter has what? Smaller what? Particles. I want to see your faces. You're hiding behind. Move like this. Michael, move like this. Shift a bit. Come to the middle. Move like this a bit. I like seeing the faces of my students. Let me know when you are sleeping and when you're doing anatomy. Move like this. Thank you. That's a better sitting arrangement. I look at you, eyeball to eyeball, I know what you are doing, whether you are following or not. Now let's continue. So, a lot of research work has proven that matter is particulate in what? Nature. And matter has what? Particles. Am I communicating? Now, so this is where this issue of atom came from. Actually, the word atom was first used by an ancient Greek philosopher by the name Democritus. He was the first person that actually tried to find out about what, at least from his work, that other scientists started coming in. John Dalton started coming. You know, I discussed Dalton at atomic theory, but it was actually the Democritus that actually started the work on what? Atoms. Yeah. Philosopher. A Greek what? Philosopher. You know that philosophy is the mother of all disciplines. Have you heard about it before? Before, during the ancient Greek era, and before now, this thing, they are not like sciences. Everything is what? Philosophy. Everything is what? Philosophy. Am I communicating? So in that philosophy, you start seeing mathematics and different aspects. Okay, what is it? Stand up. Also, front up. Stand up. Why are you sleeping? Why closing your eyes? No, that's wrong, please. I don't take that in my class. If I feel sleepy, just get up and walk around. I'll permit you to do that, but don't sit down and be sleeping. Now, let's continue. Before everything was under what? It was actually medicine. Medicine was the first discipline that got separated from what? Philosophy. Medicine was the first discipline that separated from philosophy. So from that medicine came out. From there, under medicine, other like pharmacy, different became developed, different areas of medicine developed. But it was medicine that was actually the first discipline that left what? That became established as a full discipline from what? Philosophy. Now, so let's continue. That's very well. Now, see what the guy was like, okay. And if you get a piece of substance, a piece of any substance, for example, yam or what have you, and keep cutting it, you divide it into two, and keep dividing that, divide in half, get quarter, keep dividing the quarter, and keep dividing. He was opinion that if you keep dividing that yam or any substance, divide it and keep dividing, to get to a point where you cannot do what again? Divide it. So that's where you say, okay, if that is the case, this part that cannot be actually what? Divided. That's what where the name atom came from. Am I communicating? Yes. Now, but with that now, other scientists started looking at it.
Can you see atom?
Huh?
Can you see atom?
Can you see?
Can you see atom?
No. You will say that as that is that how this discovery come. It's not what you may see something today. Stop where you can explain. Others will come up and take it up and start working on it, and discover something else that you could not see when you did your own. They keep building upon other. He just proposed that smaller one that he was opinion that smaller one, that smallest one that you cannot divide again is what? Atom. That means he was able to even see it again, and you cannot divide it now. He called it what? Atom. But that's not enough. They were making they made do with that one and in that era. Did you know when it happened? But with time, different scientists started coming up and keep working on this same thing this man did, and here we are today. Are we together? Here we are today. Before then, was there anything like you are here calling somebody on phone, using your phone to be seeing the person you are talking to? But with time, different people started working on this electromagnetic field, and here we are today. You can be here and call somebody in the US, not just on phone. You can see the person and see what the person is doing. Do you know how many years it took to get to this level? So let's continue. Now, with that now, he came to a conclusion that matter has what is called particles. Other scientists started coming up with different work to show evidence that matter actually has what? Particles. Now, from the physics perspective, I'm not going directly deeply to what we discuss in what? Chemistry. I'm coming from the physical perspective. Are we together? Now, This what happened when they now that this man known as you heard of Brownian movement, right? Brownian movement. Robert who? Brown, right? Good. Robert who? Brown. Now, according to his work in 1827, trying to also prove that actually molecule that matter has what is particulate in what nature. He proposed. He carried out different research. First of all, he used what is called pollen grain. You know pollen grain, right? Pollen grain. He used pollen grain in water and observed the movements. I realized that this pollen grain is having a zigzag movement. Am I communicating? Has what? Zigzag movement when viewed. Why that zigzag movement? There is something in that water that is knocking hair out of this pollen grain. Because it's light. Hope you know. Pollen grain is what? Light. Who has seen pollen grain here before? Have you seen pollen grain before? It's light. That's why it can move in the air. True of us. It can scatter. Am I communicating? Now, in that water, that's the first thing he did in the water. He discovered that the movement is not coordinated. It moves randomly. There is something heavier, probably, than that pollen grain inside that water that is hitting it from different direction, that is making it to move like this, move like this, move like this. There's something, because if there is nothing there, if it's truly free as it appears, the water molecule, it appears clear, right? If it truly clear as it is, then there's nothing inside that water molecule. The pollen grain would have just stay right on its own without any issues. But that's because of the light nature of that pollen grain is highly, the density is very, very, I don't know, it's light. It without that movement. That movement was named what? Brownian what? Motion, or Brownian what? Movement. Now also, even in the air, even if you suspend, if you get touched now, maybe this place is locked, and through the window you focus a beam of light through the window. Or you can even, if you stay outside here and see where the beam of light enters a room or whatever, if you look through that beam of light, you see some particles dancing in that beam of light. Am I communicating? What happens is this: these particles are very light, maybe dust particles, or they are dancing. What makes these particles to be dancing in that zigzag manner? The air, molecules of the air are hitting on these what? Dust particles. That's why they're having the uncoordinated what? Random what? Movements in zigzag what? Fashion. So this is a very strong evidence to the fact that matter has what? Particle. It's not the particle of dust we are talking about. Is what is the air is air matter. It's air matter. Air is a matter. Are you aware that air is a matter? Are you aware? Good. Now, but the particles of the air have okay. Says who? Says who? It has mass. You can weigh it. Who supporting that air doesn't have mass? Okay. Are you all against him? No. Fifi. Does air have mass? Chibuzo, does air have mass? Eh? Chemistry, does air have mass? Do you not agree with us? Yeah, you ask me the mass. Don't you know a lot of gases suspended in the air? You know, air is a mixture. So how can you ask me such question? What is the mass of air? Is air a compound? It's a mixture. So does air have does a mixture have a specific mass? Huh? So why asking me what's the mass of air when you know that air is a mixture? You can determine it by yourself. Am I complicating? You can do what? Determine it by yourself. You can determine it. You can weigh it. You get the mass. Get a tire. Get a flat tire. If you can weigh the flat tire, flat tube without anything inside it, weigh the tube empty, the way it is. Check the what? The mass. Pump it with what? Air. Check the mass again and check and know that you have. Check the difference and know that you have the same thing. Do you think you have the same thing? Get to your football, fellow you play, or even health. Lose it. Bring out the air, press it, weigh it. Take it to where you pump it. Pump it very well, health. Pump it very well. Weigh it again. Subtract the difference. Get the difference. Know that you have anything. If you're able to get any mass after subtracting the mass after pumping and mass before pumping, then whatever the difference is, give you the mass of the air you pumped. Is it making sense to you now? You can try it. It's simple. At least you play football. Try it. You may or you may not get any weight or any mass. But if you get any mass, that means air has mass. We are scientists. Try it. You can carry out a simple experiment in your house. Simple. Do it. This is how you appreciate what you study. If you read, you try to see whether you can use anything around you. You can lay your hands on and practice these things. You are developing your research acumen. You don't just cram. Alright, let's continue. Now, is this air? Is this particles of the air? Particles of the molecules of element. You know, if you say particle can be atom, it can be what? Molecule. Hope you know. Are you aware? You say particle of a matter, it can be what? Atom, it can be what? Molecule. That's why remember we said in our chemistry. I've been trying, I've been trying as much as possible not to bring the way it is in chemistry here. I'm trying, but I have to do it. Listen carefully. Remember, we talked about components of what? Matter. What matter is composed of. That's the particles of what? Matter. Am I communicating? Then we talk of what? Atoms, molecules, and what? Ions. Remember that. Now, is this atoms and molecules? Well, because in air you talk of the molecules as they are. The air is composed of molecules of different elements. Am I communicating? They are hitting on this, and they are actually what? Moving in the air. They move in the air. Air is a medium. They move, and is this movement bombarding these particles? Is this thing you see the particles of dust particles or smoke moving like this? Is the molecules or particles of the what? The the air itself that is hitting on them, because they are heavier than the particles. As they hit this side, they bombard this side, it shoots like this. They bombard this side, it shoots like this. This is what it keep doing. It's also a Brownian what? Movement. It's an evidence. It's an evidence of the what? Particulate nature of what? Matter. Now, having mentioned that atom molecules are particles of a what? Matter, even ions. Now we also talk of what is an atom. We still using the definition of we said that atom is smallest indivisible particles of an element which can take place part in a chemical what? Reaction. Now, let us describe the atomic structure. Remember where we started? We started with matter. We defined matter. We now came down to what? Particulate nature of matter, trying to use the work of Robert Brown in 1827 to prove that what? Matter has what? Matter is particulate in nature. And these particles we are talking about are what and what? We talk of what? Atoms, right? Molecules and what? Or ions. Now, let's focus on atoms and what? Molecules. Now, we are talking about what now? Atoms. And we are defining atom. These things are not new to you. Now, atom now, if you go now go down to we want to look at the structure of what? Atom. I mentioned it in our chemistry class, but I'm going to talk about it again. Atom is made up of what? Two parts. You have the what? The nucleus, the nuclear part, and the what? The shell, right? So in the nuclear part contains atom itself has other we call it them subatomic what? Particle. We call them sub because they are inside atom. They are in the atom. They make up the atom. Subatomic particles. The major ones there. We talk of the what? The proton, the neutron, and the what? Electron. Now, the proton and the neutron come together to form the what? They are found in the where? The nucleus. Are we together? They are found in the nucleus. While electron revolves around the shell. Am I communicating? Now, there is this type of force that exists between the. Okay, let me talk about the charge. The proton is positively what? Charged. You are not putting out anything. You already know it. Okay. I like that. Until I ask question, then I know that you actually know it. Then the proton is positively what? Charged. Neutron has no charge. Because the proton is positively charged and neutron has no charge. So two of them that makes the nucleus to be what? Positively charged. That makes the nucleus to be what? Positively charged. Because proton and neutrons are found in the nucleus. The nucleus is positively charged and the neutron has no charge. That's why because neutron has no charge, the nucleus takes the charge of the what? Proton, making it positively what? Charged. So the nucleus is positively charged. So anytime you hear nuclear charge is what? Positive. Is it clear? It's positively charged. Now, the electron on the shell is negatively charged. Are we together? The electron is what? Negatively charged. Please, by the time we discuss Bohr's atom, Niels Bohr's model of the atom, we know that this thing we say shell is not only one shell. It can be up to 1, 2, 3, 4 shells, and they are quantized. I don't want to go into that. We'll still go into that quantization of these shells, the different quantum numbers, and which we see discuss that. But just know that they are quantized, that they're not at the same level. They are different. All these shells are in different energy levels. Okay, we discuss that when we go interior. Now we are just talking about the physical. We are not going interior. We go interior in chemistry. Now the electron being negatively charged, the neutron, the shell, the electron in the shell being negatively charged, and the nucleus positively charged. There is this force of attraction between the electron in the shell and the nucleus. Is this force of attraction that holds the electron in this outermost shell without it falling off. Because of the attraction, the nucleus will be attracting the electron. They will be attracting. That force of attraction keeps the electron in the revolving in the outermost shell. If there is no such attraction, the electron will not be revolving in the outermost shell. On the shells. Are we together? Now, an atom is electrically neutral because there is this force. The number of proton and number of electron in an atom, they are equal. In an atom, the number of proton and number of electron are equal. That's why we say that an atom is electrically neutral. It has no charge. An atom has no charge. An atom has a charge, gains a charge if it forms ion. But the type of charge it will form depend on whether it gains electron or it loses electron. Now, nucleus is heavy. The nucleus is heavy. Hello? The nucleus is heavy. The nucleus is heavy because of the weight there. The weight of the nuclear proton there is almost 1/1840 of the weight of electron. Electron is relatively light. In fact, the weight of electron is negligible. It's in the order of minus 31. 3 square minus 31 is negligible. Electron is the weight of electron is negligible. That's why, in fact, you rarely hear of weight of electron because it's negligible, and that's why electron can easily be transferred from place to place. Are we together? Because the weight is not heavy, unlike proton that is heavy. Does it make sense? Unlike proton that is heavy. Does it make sense? Good. So please note this point. Note this point. What did I say now? That proton is what? Yes, sorry, weight of electron is 1. I mentioned a figure. 1 over of what? Proton. Is that what I said? That the weight of electron is 1 over 1,840 of the weight of electron. Is that what I said? What did I say? No. Normally, weight of electron is in order of 3 minus 31. It's negligible. Electron is very, very light. Its weight but when compared to proton, the weight of electron is about 1 over 1,840 of the weight of proton. Do you know what it means? You divide proton into 1,840 pieces. One of it, weight of electron. Does it make sense? If you say that my weight is 1 over 2 of your weight, what does it mean? You divide your weight into 2. If you say that my weight is 1 over 2 of the weight of, what does it mean? That means you divide the weight of Izu by 2. One of it is my weight, 3 of us. Now, if I say that the weight of electron is 1 over 1,840 of the weight of proton, what does it mean? You get a proton, get any weight of proton, get proton, divide it into 1,840 pieces. One of it is weight of what? Electron. It's not very too light. Very, very what? Light. That's the meaning. That's what you're talking about. We will discuss this in detail when we go into the works of these scientists in atomic structure. Remember, we in chemistry here. We are discussing atomic structure. Remember, when we go deep into that, we will see how this experiment we are carried out, how works of Millikan, Chadwick, and others. We discussed that one in detail. But I just want you to know that the weight of electron is 1 over 1,840 of the weight of what? Proton. So electron is very, very what? Like that's why you can easily transfer electron. Have you ever seen that? Hear that doing ordinary chemical reaction? Now proton is transferred. It's electron that easily do what? You lose electron and gain electron. Formation of ion is all about electron what? Movement. That's why they what's that? The weight of proton. Good. Weight of proton is around if weight of electron is almost, I think it's 9 times 10 power 31 or so. Weight of electron, something like that. I think so. It's from this work that if that is given now 1 over 1,840. If this is weight of electron, I think it's around 9 times 3 power minus 31, something like that. Now, if this weight of electron and this is 1 over 840 of what? 1 over 840 of the proton. So that means 9 times 3 power minus 31 is equal to 1 over 840 times what? Weight of proton. Okay? So that means weight of proton is what? Multiply this by this, you get weight of proton. Are you there? Are you there? Are you there? Good. Yeah. Yes, because of yes, of course. The charge there in the nucleus is contributed by what? Proton. Because neutron is neutral. So you just between the attraction in between what? Electron and proton inside the what? Nucleus. Is it clear? Is it clear? Good. Huh? It has name. What that? It just is electrostatic force of attraction, something like that. Yeah, that's the electrostatic force of attraction. Okay, between the electron and on the shell and the what? The positive what? Nucleus. That is proton in the shell. By the time we go into atomic structure and chemistry proper, you understand it. I'll take time to explain this better. Now, so now you now have an overview of what atom looks like, right? Right? Good. Now let us now take a look at the molecule. Take a look at the molecule. Let's take a look at the molecule. Okay, we'll see after. Now, just as we have atom is a particle of a matter. We also have what? Molecule. Now, actually, what happens is this. You know, some atom cannot exist on their own. There are some atoms that can exist on their own. Something like sodium. Sodium atom can exist on its own. Are we together? Are we together? But there are some atoms that cannot exist on their own. Oxygen atom cannot exist on its own. Are you aware? Are you aware? Good, I will explain. Hydrogen atom cannot exist on its own. That's why sodium can exist on its own as sodium atom element. But oxygen normally appears in two, diatomic. So oxygen can combine with another oxygen to form O2. That's why have you ever seen oxygen repeating like O? On a normal is what? O what? 2. We will still discuss this in chemistry when we talk about atomicity. Are we together? Diatomic, the one that are diatomic, monatomic. So oxygen is diatomic. Oxygen molecule is diatomic. So when oxygen atom combine with oxygen atom, a molecule is formed. It's a molecule. So you say oxygen molecule. Am I communicating? So one oxygen molecule has 2 oxygen atoms. Okay? Okay? So one hydrogen molecule. I'm trying to draw a line between molecule and what? Atom. So if you see something like this, if you see something like this, hydrogen cannot exist like this. This hydrogen atom, but in nature, it cannot exist like this. It normally combines with another oxygen atom to form oxygen molecule. That's why you see oxygen like this, H2. That's how oxygen appears in nature. So I mean hydrogen, sorry, don't mind me. You know, sometimes the brain will say another thing, the mouth will say another thing, the hand will write another thing. Hydrogen atom appears in nature, H2. This is a molecule. This is what? An atom. This is an atom of hydrogen. This is a molecule of hydrogen. So a molecule of hydrogen molecule has 2 atoms of water. Hydrogen. Does it make sense? This is not chemistry. I'm doing this as this is chemistry. I don't think you do this. What it is. You work as a person. Okay. This is physics. Physics, you don't go deep like this, okay? It's chemistry that you start breaking down like this. But I just want you to know what we mean by this. This is an atom. This is a what? In nature, hydrogen appear like this. The same thing with oxygen. The oxygen doesn't appear like this. In nature, it's like this. It can't exist as atom. No, it cannot. That's why they form that molecule. And have you seen sodium like this before? So sodium doesn't exist like this on its own now. So sodium can still stay like this as sodium. It's an atom. Sodium, this is atom. This is an atom. The only thing it can do now is it can undergo what is called. It cannot combine with another sodium again to form sodium molecule. What it can do is to form sodium ion, either gain an electron or what? Sorry, it will lose electron, not gain. Sorry, it loses electron, right? We will see discuss this in chemistry. That's why I'll be trying. If you're following me, if you're listening to me now, you know that I will just go straight. I'll go a step deep. I'll come out again. I don't want to start going to chemistry because I was end up teaching chemistry. This is physics. This is just to mention, to try to talk about matter enough. Physics doesn't go so deep into this level. Okay? That is chemistry. We do it in chemistry. Now I just wanted to have an idea of what molecule look like. Now, the same thing with chlorine. Chlorine doesn't exist like this in nature. It's chlorine. It must combine with another chlorine atom to form what? This is chlorine molecule. Okay? So a molecule of. So the point I'm making is this: a molecule may have you may have a molecule form from the same atom. That's the point I'm making. A molecule you can see a molecule of the same atom and molecule of different what? A molecule from the same atom of what? An element. And we can also have molecule formed from different, yes, entirely. Water is a molecule. It's not a molecule, water molecule, but it's formed from where? Oxygen and what? Hydrogen. Because it has different atoms of different elements, true or false, but it's still a molecule. So oxygen molecule is formed from where? Two oxygen what? Atom that form the what? Oxygen what? Molecule. That's the point I'm trying to make. So you may have a molecule of the same element whose atoms are of the same element. We have a molecule that have different distance. Are we together? Are we together? Are we together? Now, can you hear me? All right, let's continue. Now, so what is this molecule? What is a molecule? What is a molecule? It's a molecule. Anyway, I like that, but can you define molecule? Just as atom is smallest, right? That definition. We know that we go deeply. That is somehow wrong, but they still carry it on in physics. Because that physics that they are not going so deep, unlike what? Chemistry. Now, a molecule is the smallest what? Particle of a substance that can do what? Have a separate what? Existence and still retain the properties of that what? Substance. A molecule is the smallest particle of a substance which can have a separate existence and still retain the properties of the what? Of that substance. Sorry, our reference book for today is in New School Physics for Senior Secondary School 2016 edition by Professor M.W. Anyakoha. This is our reference book for today. Now, as I said, a molecule is the smallest particle of a substance which can have a separate existence and still retain the properties of that what? Substance. I think I have explained that a molecule may contain similar what? Atoms, right? I gave oxygen molecule as an example. I gave hydrogen molecule as an example. Even nitrogen N2. Nitrogen molecule is N2. Are we together? You can say a molecule can exist. A molecule may contain similar what? Atoms. Example: oxygen atom O2, nitrogen N2. Hydrogen, H2. At the same time, the molecule can have what? Different what? Atoms. Example: water, H2O. Ammonia, NH3. Ammonia, NH3. You can also add chlorine. A molecule that have similar atoms. Different atoms. Ammonia, water. There are many of them. Okay, now not all substances. This is a compound, I hope you know, but not all compounds exist as molecule. There are some compounds that exist as ion. Okay, not all compounds exist as what? Molecule. But by the time we go into chemistry, chemical bonding, you understand it better. Okay, Let me not go there. Now, this example too. Now, there are different experiments that have been carried out to determine the size of what? Molecule. Now, in the year 1890, a scientist known as Lord Rayleigh, Raleigh, in 1890, he estimated the size of a what? Of a molecule. See what he said. He said that the size of a molecule, like now, that if you pour something like oil, you are writing Lord Rayleigh in 1890. He's the person that estimated the size of what? Of a molecule. Lord Rayleigh, Raleigh. See what he said. That if you want to determine, like now, oil now, for if you use something like oil, you want to get the size of the molecule of oil. See what he said. And if you just pour the oil on the water surface, the oil will spreading, right? The oil will what? Spreading. And when the oil end up spreading, if you finish spreading, that the thickness of that oil film on the surface of that water is the size of the molecule of that what? Oil. Is it clear? That if you pour this water now, maybe in a tumbler or something, and pour oil, or maybe in a bigger issue, and it keeps spreading on the surface. Have you noticed it before? Now, when it's done spreading on the surface, the thickness, you know what is thickness now? If you get the glass, you can see through the water, you see thickness of that oil on top of it. That thickness, you can use that thickness to determine the size of the what? Molecule of the what? Oil. Now, they now carried out research. With this now, you can carry out a research. It's simple. You get maybe a triangular or rectangular basin or something, and fill it with water. Then you get a pipette. You sprinkle a lycopodium powder on it, maybe to enhance the surface area or so. But when surface tension, are you there? Now, when that is done, if you pour oil, first of all, you don't pour oil. You use pipettes to measure a specific volume of oil, and they spread it on the surface of the water. And when this is done, you can actually, since you know the volume of the oil, right? Then you can check the diameter of the oil spread. You check the what? Diameter of the what? The oil. You can also check the what? The thickness. Now, when this is done now, you are good to go. You can use this formula. Sorry, unlike micrometer screw gauge, you can use the thickness. You will not actually be able to take the thickness of the what? Oil on top of the water. So what you can do is easily do is this. If you take you know that it will spread as a what? As a sphere, right? On the oil. It will spread. If you view it from the top, you see something like this. Hope you know. Hope you know. Are you aware that if you view it from the top of this, you get something like this? You can actually measure the diameter of the oil spread. If you measure the diameter of the oil spread, we call it what? D, right? You already know the volume. You already know the volume of what? You already know the volume of the what? The oil you poured, right? The oil you spread, you know, because you use pipette to measure the volume, true or false? Then the volume is there, you know the volume as V. You know the volume as V. This water is affecting this matter. You know the volume of the oil you introduce on the surface. You know the volume of the oil you introduce on the surface as V. And you check the diameter of the oil spread, right? As what? As what? D. Remember? Now, but what you want to determine is the thickness of the what? Thickness of the oil's film. Because according to Lord Rayleigh, that thickness gives you the what? The size of the what? Molecule. Am I communicating? Now, you know the volume of the oil you poured, you know the diameter of the spread. Now, remember that this will form a what? A sphere, right? A circle, sorry, right? Right? Now, what is the area? Area of the circle is what? Area of the circle is what? What is area of the circle? Pi r what? Good. So we can determine the area comfortably. True or false? Area of this circle is what? Pi r what? Square. Is it not? Is it not? Good. Remember that radius is diameter divided by 2. Hope you know. Hope you know. Who doesn't know? That radius is the diameter divided by 2. Who doesn't know? We all know, right? That means we can replace this radius with what? D over what? 2. That means the area of this oil film is what? Pi what? D over what? 2 what? All squared. This is the area of this what? Oil film. Oil film. Now, this is area. Now, we know the area. We know because we have measured the diameter. We know we can now determine the area. We can leave this formula like this. Now we go back. Remember the volume. Remember the relationship between volume, thickness, and what? Area. Remember that the volume is what? Area times what? Times what? Breadth. That's the what? Thickness. Hope you know. Are you aware? Are you aware? Are you aware? That is what? The thickness. That's what we talk about here. Area times what? Thickness. That means thickness is equal to what? Volume over what? Over what? Area. So if you want to determine the thickness of this oil film, we put it here. We only know the volume, right? Which is V. The thickness of the oil film, which is set as the what? The size of the what? The molecule. Are we there? Is now equal to the thickness, which is size of the molecule, is now equal to the volume, which is V, over the area, which is what? Pi all squared. Are we together? So we can now transpose this and get something like this. Remember that this is something as saying V over what? Pi what? D square over what? Over what? Over what? Which is what? 4. True or false? Remember law of fraction. This thing should come up. True or false? So this is just now saying this is now 4V over what? Pi what? D square. This is the thickness of the what? The oil film. And this will give you the size of the what? The molecule. So the volume you poured, you fix it there. Divided by the pi is constant, right? Times d square. This one is diameter squared. If you calculate it, it will give you the thickness of the what? The film. And this will give you the size of the what? The molecule. Does it make sense? Does it make sense? So this is what this man did. This is what this man did. And this is what they use to determine the size of the what? Molecule. I'm just giving you an idea of what has been so that you know how far these people have gone determining the size of the what? Molecule. Are we together? So this thing is in what? Cm, because the volume here is in what? Cm3. This diameter is in Cm. The volume is in what? Cm3. That means this thickness is in what? Cm. The thickness is in what? Cm. So with this thing now, accurate experiment will give you the thickness of oil film around 2 times 10 to the power minus what? 7 cm. It will give you the thickness of the oil film around what? 2 times 10 to the power minus what? 7 cm. Around 2 times 10 to the power. So this is taken as the what? The size of the oil what? Molecule. Are we together? Are we together? Good. So I remember I told you something about putting torch, watching, observing particles when a ray of light enters a room or leaves a room. If you follow that ray of light, you start seeing what? Just get torch now, spread torch across. Either inside this place or as if you are going outside. If you see that particles of dust particles or particles of anything that is suspended in the air, you see it dangling. You've seen such, right? Now, this experiment was also to prove this thing. They carried out experiment using what is called smoke cell experiment. Smoke cell experiment. This is exactly what they discovered using smoke cell what? Experiment. The difference is that they use a small cell, a cell they call smoke cell, and suspend particles inside it. Then they now use lens. Who has seen lens before? Lens in your physics practical. They now use lens and focus. You can use lens and focus light inside that what? Inside the cell, and use microscope to observe movement of these particles. That's how they prove that actually this is what is actually happening in this place. That is molecules. It's molecule of the air that is causing that what? Dangling. These particles to be moving because the molecules of the air are hitting on these particles and they are doing what? Showing that zigzag what? Movement. Does it make sense? So that movement is not about the particles you are seeing with your eyes. It's the particles of the air you are not what? Seeing. That is hitting on the dust particles you are seeing that are moving around. Does it make sense? Does it make sense? So this is a proof there is something hitting it you are not seeing with your eyes. But this microscope exposed a lot of things. So this is what they did using what? Smoke cell what? Experiment. So smoke cell experiment can also be used to prove Brownian what? Movement. It can be an OBJ question. Which of these remember you see smoke cell? In case you see it, don't be shocked. We have not seen this one before. Smoke cell experiment. So you don't feel maybe, hey, I've not heard about this one before. Smoke hyphen cell. Smoke. So they use smoke to carry out the what? Experiment using that box called smoke cell. Smoke inside, they now focus light on it. Using microscope, they are viewing what's going on in that smoke cell. They now observe that zigzag what? Movement of the smoke particles. Does it make sense? So this is what happened. Now, what with all these things I've been talking about, what if you are asked now define Brownian motion, what are you going to say? Remember Robert Brownian. Is Robert Brownian a botanist too? A botanist. Remember how the first experiment he did, he used what? Pollen grain from plants. He's a botanist, okay? He was a botanist. That's why he could work with what? pollen grain from where? Plants. So Robert Brown was a what? A what? Botanist. A botanist. This happened in 1827. So how can I now define Brownian motion? Who can now define Brownian motion for us? Brownian motion is what? Who? Help us. Huh? Huh? Good. Brown, good, I like that. But it's constant. Brownian motion is a rapid. Brownian motion is a rapid, constant, and irregular motion of tiny particles. Simple. Brownian motion is what? Rapid is a rapid, constant, and irregular motion of tiny particles. Remember we said that this motion was first carried out using pollen grain, remember? Using pollen grain in water. So with microscope he was able to discover that movement. That's why there's something in this water that is hitting this particle and making it to be dancing like this. Are we together? Good. Now, what time? Is this 6 o'clock? It's not 6 o'clock, right? We have 6 minutes. Now, let me round up. So I want to finish that, conclude with Brownian motion, talk about the diffusion. In our next class, we start with states of where? Matter. In our next class, we start with what? States of matter. In our physics assignment, you are asked to define diffusion, right? Have you seen why I gave that assignment? Good. So, please ensure you do the assignment. Don't sleep on it. Do all the assignments you are given. Because in the next class you come out here and present. You know how we review our assignment now. You know how we do what? We review our assignment. If you do your assignment, you come out here. If you watch now, I've been teaching, right? In review, no teaching. I'll sit down and teach me. That's how we roll here. During review, I will not teach. I will sit down like a student. You do what? You teach me. So do your assignment properly with your full chest. I think it's better we even stop yourself and start from diffusion. Sure? Yes, you are tired. Why do you get tired easily? Are you that weak? Sit up. You are fragile. Sit up. You don't be fragile. The world is so tough that you don't be too fragile. Don't be fragile, man. Now, is there anything? Any questions so far? Any questions so far? Huh? Good. So, Brownian okay now, application. Yes, write that please. Applications. Applications of what? Brownian, or importance of what? Brownian motion. Number one, there are two importance I want to talk about. Number one, it gives evidence for the existence of what? Tiny particles of molecules of matter. It gives evidence. It gives evidence for the existence of the tiny particles of matter called molecules. So that means Brownian motion helps us to prove that there is what? Molecules. True or false? True or false? True or false? True. Because it's that molecule of this matter that is hitting those particles that is dancing a willow. Even though our willow is not a zigzag the dance. Like like a drunkard. I think they do this. Those particles are small particles that are dancing like drunkards. The drunkards take zigzag what? movement. They have no direction. So this banana movement is important to evidence to prove that molecules exist. True or false? Good. Now another importance is that it helps to prove that these molecules are in constant random motion. Yes. It also helps us to prove that these molecules we know that exist are in what? Constant random what? Motion. These are very two importance of what? Brownian what? Or Brownian what? Motion. It proves that molecule exists, that these tiny particles called what? Molecule. It also helps to prove that these molecules that they are in constant what? Random what? Motion. That's what Brownian movement helps us to what? Prove. There are other natural phenomena that also explain these movements. Phenomena like diffusion and osmosis. These phenomena like diffusion and osmosis also prove that molecules exist. That is because of, listen carefully, it's because of the movement of this molecule that you stand on this door and mess and release poisonous substances from your bum bum, and we are here, we perceive it from here. Something you did here, thinking that nobody will know. Under 5-10 seconds, we will do what? It will get a how. Is the particles of the air that will carry it, these molecules, and dangle it, and dangle it here. I will perceive it. Does it make sense? So this will form our next topic, diffusion. Any question? So in the absence of any question, our weaker sister is saying no, that we should stop here. As she said that she's fragile, our fragile sister. So we'll stop here for the benefit of our fragile sister. We'll stop here and continue next week. Hope you enjoyed the lecture. Hope you learned something. You didn't enjoy the lecture. Why? It's boring. Yeah, but you understood it, right? Good. That's the most important thing to understand. There's no other way you can understand the Nablo in and again. You listen. So maybe next week now, you can now come here and teach me. I'll sit down. Don't make your own boring. All right. Thank you very much. See you next week. God bless you.